Dr. Matthew England is both a great mathematician and a great computer scientist, and is a known face in computer algebra, especially the topic of cylindrical algebraic decomposition. And I was lucky enough to have the opportunity to join his team from 2021 as a research fellow, a postdoc. I had 3 years postdoc experience with him, and now even I'm assistant professor. I'm still in his team, which is a great thing for me because he is a very kind and helpful person. And a great news for the audience, he is also a good speaker. He's going to talk about advancing computer algebra through other algorithmic domains. Dr. Matthew, please go ahead. Thank you.
Okay, can you see my screen? Is it visible? Yes. It is. Okay, great. Okay, so I'm looking at my screen, but if there's any question, Amir, just speak it, and then I can answer. Okay, so first of all, I'm very sorry I was late. I'm very happy to give this talk. So thank you for the kind introduction. I'm Matthew England from Coventry University in the UK. This bird is the phoenix. It's the symbol of the city of Coventry, and this is a nice picture of the Coventry skyline. We are oh, sorry, screen just froze. There we go, it's back. Okay, so I'm going to talk today about computer algebra, but you know, I've got a slide before I begin to try and reflect on this online conference, which I know is motivated by the famous Persian scholar. I'm not sure I'm going to say the name right, but I'll try. Al-Khwarizmi. Did I say it right, Amir? Probably not.
Yes, it's fine. Yes.
Okay, so you know, this conference, I was reading the information about the motivation here, and I really like it because it really links to what I wanted to talk about. So this scholar is famous for many reasons. In particular, as it said in the conference website, he gave his he gave the name algorithm to the world from the text he wrote introducing the Arabic numeral system to the West. This was good because the Arabic system was much easier to do arithmetic in than the systems being used in the West, and you can do it more algorithmically if you like. What it didn't say on the conference website, but I'd like to just remind the audience, is that he also gave his name to algebra. So he wrote a text on how to solve basically what we would now call linear and quadratic equations, and the abbreviated name of that text was algebra, which has led to the modern word algebra that we use. And my talk today is going to be on algorithms for doing algebra. So it's kind of on two topics, both of which relate to this great scholar. Okay, so I'm going to speak about something called computer algebra. So I better say what that is. It's simple to define. A computer algebra system, or a CAS for short, is a piece of computer software for manipulating mathematical expressions and objects. And this is different to the more standard computer software you may be useful because it's really about the mathematics. It's about exact answers. It's not the more common numerical computation or floating point arithmetic. So as a simplest example, a computer algebra system would compute with the symbols 1/3 pi and square root of 2 rather than their decimal approximations given there on the slide. So it's maintaining the accuracy that's not possible because we cannot have infinite decimal numbers in floating point arithmetic. But something that sometimes surprises people if they've not looked at floating point arithmetic before is that even when one does floating point arithmetic with finite decimal numbers, it's still inaccurate. So here you have the most common programming language in the world, Python, a screenshot of the Python interpreter installed on my computer. And if I do 0.1 plus 0.2, Python will tell me the answer is 0.3, followed by many zeros, but then with a 4 at the end. So this 4 is an error. It's nothing wrong with Python here. This is simply what you would get if you do floating point arithmetic. It boils down to the fact that although as humans, we're used to thinking in tens, in the decimal system, what the floating point arithmetic implements is suitable for computers on chips, which think in base 2. And so some numbers which are able to represent finitely in base 10 are not represented finitely in base 2. And so we have this error here in this case. So, you know, is this error a problem? Not usually, depends what you're doing, but in some situations we might want to avoid such errors. So there's rules for adding fractions like a third. you will have learnt them in school, I have no doubt. What you probably didn't learn in school, but I tell you exists, is that there's also algorithms, rules, if you like, for doing arithmetic with algebraic numbers. So algebraic numbers are numbers defined as the root of a polynomial. So a classic example is the square root of 2. We cannot write the square root of 2 as a finite decimal. We cannot write the square root of 2 as a fraction, as one integer divided by another, but we can still compute with it with exact precision using the theory of algebraic numbers. And essentially, it boils down to us manipulating polynomials instead of manipulating numbers in order to do that. Just as a side note here, this is one of my favorite pictures. It's on the Wikipedia page for algebraic numbers, and it's simply a plot of all the algebraic numbers computed within certain ranges, and you can see they kind of cluster around each other in this way that almost looks like we're looking into space. Okay, so why might we want to avoid these errors? So I'll try and give some motivation. So first example is sometimes there are problems that are ill-suited for numerical computation. Situations where you can have a small inaccuracy in your system and it then leads you to a completely different answer. So I have here a screenshot from a paper I wrote maybe 10 years ago. And I won't go into the details, but it's essentially modeling some biological system. And the pictures on the bottom with the blue and yellow dots, these are computed using computer algebra, and they're exactly correct, by which I mean the blue dots are definitely blue and the yellow dots are definitely yellow, where these represent some biological property. The ones on the top row were computed using a leading numerical solver at the time, and you can see they mostly get it right, mostly yellow and blue, but there's also some red dots, some green dots, and these are simply places where the solver gave the wrong answer because these small errors in the floating point arithmetic all kind of roll in together to end up giving the wrong answer to the biological property in the end. So there are some systems where, yes, where you need the algebraic tools to find out the exact answer. There are also, of course, some systems where we simply will not tolerate any risk, even if it is very small. So we have here a picture of what's called the Canada arm that's attached to the International Space Station, and the code that decides how to move that arm is computed not using floating point arithmetic, but by using computer algebra, simply because they're not willing to tolerate even the tiniest error when the life of an astronaut is in the hands of this arm, as you might expect. And then this is an example. I didn't ask his permission, but this is an example from your host, Amir, one of his papers, but it's one of my favorite examples. So what Amir did here was he took a biological problem and he studied it using algebraic tools and using numerical tools. And I'm not going to go through what the different colors mean, but again, they mean biological properties. And one of the interesting questions that Amir was looking into was if he was to fix the parameter b and increase the parameter a, does this, in this case, it's the number of steady states of this biological system, does it always decrease? And you can see from the numerical plot here, it looks like it does. If we look at, for example, b equals 0.3, and we increase a, it starts off at 27, then goes down to 21, then 15, then 9, then 3. So it looks like this is the case. But when using the algebraic tool, we actually see it's not the case. There's this area, it's a zoomed in portion of this plot, where we have this situation that as we increase a, it goes 15, 9, and then 15 again. So it reveals essentially a fundamental insight that was missing from the biological hypothesis, essentially proving that what the biologists had assumed could happen in this system wasn't always the case. So it makes us then re-question some of the earlier assumptions, and this is only possible with the kind of high or exact precision of the polynomials that which allow us to search exactly for situations like this. If we were just to do random numerical sampling or numerical computation, the errors might crowd out that precise information. So what is it that computer algebra research involves? This is just some high level kind of insight. So you might see if you're interested to pursue this. So it kind of involves a couple of different things. It's not really one field. It first of all, it involves computer science. So computer algebra, you have to invent algorithms, ways of doing things, data structures, ways of storing this data, implement it, optimize it, evaluate it. This is kind of core computer science. So for example, you know, these polynomial expressions usually are encoded in some kind of expression tree like this. So what kind of data structure do we use for that? But also this involves a lot of mathematics. So any algorithm that we write for doing computer algebra, we should also prove mathematically that it's a correct algorithm, that it does what we claim it does. And it's not enough to just to show some tests that the algorithm works. Look, it works for this example, that example. What we really need is mathematical guarantees that will always work. And this requires formal mathematical proofs. So, you know, computer algebra is actually one of the earliest forms of computing. The first pieces of software were released in the 1960s, not long after the computer was invented, but it's still a very active area of research today. So me and Amir, indeed, work on UK government-funded research projects in this area, and I acknowledge that here on this slide. Okay, so now I've given an introduction. I want to talk about a specific problem, which is an area of research. So this is something that we try and work on, but it's also, I hope, able for anyone to understand if I explain it well. So let us hope that I explain it well. And if I don't explain it well, please do ask questions and I'll try and explain better. So the only kind of mathematical knowledge that you really need here that you may not have is the idea of quantifiers. So I need to explain what these are. So you're probably from school familiar with the idea of algebra, where we use symbolic variables like x, y, z to express and model the real world. But our models can be far more expressive if we also allow, as well as variables, the ability to use quantifiers. And quantifiers are symbols or operators that specify how many individuals in the area that we're talking about that the variable is allowed to represent. So there's two main examples, and if this doesn't make sense yet, don't worry, we'll have some examples in a minute. So the two main quantifiers are the existential quantifier and the universal quantifier. So the existential quantifier, which is written in mathematics commonly as a backwards capital E symbol and is pronounced in English, there exists, we use this to say that this piece of mathematics applies to at least one individual in the domain of discourse. And the universal quantifier, which is written with an upside down capital A and is pronounced in English for all, is used to say that this piece of algebra applies to all of the possible individuals that the variable could take. So a universal statement is much, much stronger than an existential statement. And so, you know, when we apply these quantifiers to polynomial systems, equations, and so on, we are then expressing, you know, more complicated statements than we were before. But there's a really fascinating fact in mathematics, which is if you're talking about polynomials over the real numbers, then there always exists an equivalent logical statement without quantifiers for any given statement that has quantifiers. So what do I, you know, let me unpack that for a minute. What do I mean by equivalent? Well, by equivalent, I mean true for the same values. So when one is true, the other is true. And it's not obvious that this should be the case, but it was proven in the 1940s by Tarski that it is indeed the case for the real numbers. Now, the version without the quantifiers is usually much longer than the version with the quantifiers, but although it's longer, it can sometimes be easier to understand. It can sometimes be easier to visualize or plot or analyze. And so often, yeah, it may be longer, but it's simpler. Which then raises the question, how is it we can move from one to the other? And now I have some examples, which will hopefully, if you're not following this, will make it all a bit clearer. So I'm going to talk for the rest of today about something called quantifier elimination. So it's a problem where you give me a formula that has quantifiers in it, and my job is to find you a formula without quantifiers in it that is logically equivalent. So let's look at some examples. So the first example here, in the line that says input. Backwards Z means there exists. So this is saying there exists an x such that x squared plus 3x plus 1 is greater than 0. So what's the equivalent statement without a quantifier? Well, the equivalent statement is simply true, because this is a statement of mathematical truth. If you want me to prove to you it's true, I say simply think about the case when x equals 0. So when x equals 0, x squared is 0, 3x is 0, and we're simply left with the statement 1 is greater than 0, which is true. And the statement simply said that there's at least one x in the real numbers that this is true. And there is. I proved it to you here. So here, the quantifier elimination simply means to answer the question, is this possible? And it is possible. The answer is true. Let's look at a second example here in the middle. For all x, x squared plus 3x plus 1 is greater than 0. So this is a different statement. This isn't saying there exists just one x that makes this true. It's saying this is the case for all of the different real numbers that x could be. And this is not the case. If you think about x equals -1, -1 squared is 1. 3 times -1 is -3. So we have 1 minus 3 plus 1. So we have -1 bigger than 0. And that is a false statement. So we know that there's at least one x where this statement doesn't hold. And so the quantification for all, it's incorrect. So the equivalent here is false. This is simply a false mathematical statement. You can sometimes have universal statements that are true. So for example, x squared plus 1 greater than 0, or x squared for any real number is a positive number. And if I add 1 to it, it's definitely bigger than 0. So yes, this is true for every real number x squared plus 1 is greater than 0. So these three examples, the answers were either true or false. And indeed, if you have a problem where every variable in the problem is quantified, then the answer is true or false. Quantifier elimination simply means to answer whether this is the case or not. But things get more interesting if we are to look at a problem where some of the variables are quantified but not all. So let us look at this problem, which will be our main problem moving forward. For all x squared plus b times x plus 1 is greater than 0. So what is the answer here? Well, the answer is it depends on b. It's not always true. It's not always false. For some b's, it's true, and for some b's, it's false. So how might we solve this? Well, we could take a numerical approach. So what I've done here is to plot the graph of the polynomial x squared plus bx plus 1. And here it's plotted with b equals -4. Here I plot it with b equals -3. And you can see that for both of these cases, -4 and -3, it's not the case that for all x, it's positive, because, you know, the curve, it dips below the x-axis here. However, if I look at it plotted with -2, I can see it is always above the x-axis, except just where it touches there at the point x equals 1. And if I was to plot it with b equals -1, then now the entire function has risen above the x-axis, and this statement becomes true. And here it's plotted with b equals 0, b equals 1, b equals 2, and b equals 3, and now it's dipping below the x-axis again. So by making these pictures, I can see that the answer is that this statement is true if b is bigger than -2 and smaller than 2. So for the b's in that range between -2 and 2, that's a true statement. But for the b's who are more negative than -2 or more positive than 2, then it's a false statement. So what I've done here is I have eliminated the quantifier. I've taken a mathematical statement with a quantified variable, and I produced another mathematical statement that has the same truth false-ness, if you like, but it doesn't involve any quantifiers. And in some sense, the output here is easier to understand. It's telling you what you really wanted to know, which is, you know, for what b's is this problem solved. So what I do with most of my time is to build technology which can answer this question exactly. So the way of answering this question by drawing the pictures is essentially a numerical approach. Drawing pictures means crunching some numbers making some pictures, but we want to solve it exactly. We want to solve it using an algebraic approach. And the tool that can do that is called the cylindrical algebraic decomposition. So it's a mathematical object which chops up space, decomposes it into cells. Each cell is itself an algebraic cell, which simply means it can be defined by a polynomial formula. And the cells are arranged in a particular order. We call it a cylindrical arrangement because the cells sit on top of each other in cylinders. So this picture here is the green cell, the yellow cell, and the blue cell. They're kind of sitting on top of each other in a cylinder, like plates in a stack, if you will. And the CAD algorithm produces these objects relative to a given set of polynomials, meaning it guarantees that each polynomial is either positive, negative, or zero in each cell. So here the polynomial was the polynomial for the unit circle. So the unit circle is positive on the dark red cell, but it's negative on the yellow cell, for example. So why is this CAD a good thing for me? Well, the thing that's great about it is it's decomposing an infinite space. There's an infinite number of real numbers here, stretching off to infinity in the x direction, but also negative infinity in the other direction, and the same in the y. But we are boiling it down to a finite set of cells. And more than that, for each cell, we can take just one point on that cell, see what happens at that point, and basically the same thing happens everywhere in the cell. So it boils the infinite down to the finite, which is a really powerful thing. Further, the algebraic property means once we've analyzed our cells, we are able to easily extract formula from the cells that are true. And the cylindrical property, well, that makes it easy to do certain things that we'll see why it's useful in a moment. So let's look at an example problem here. So suppose I want to solve the problem, does there exist an x such that x squared plus bx plus 1 is less than or equal to 0? So here I've graphed the polynomial x squared plus bx plus 1, although b is the horizontal axis and x is the vertical axis, so somewhat odd axis naming, I appreciate. So if I want to solve this problem, this quantifier elimination problem, what do? I'm going to build myself a CAD relative to that polynomial. We'll talk briefly about how to do that in a moment, but basically I'm going to get these blue and yellow cells. I'm going to take sample points, 1 point from each cell. Those are the black dots. And I'm going to test those cells, and I'm going to color them in depending on whether or not the polynomial is less than or equal to 0. And the red cells, now colored in, are the ones where it was not less than or equal to 0, and the green cells are the ones where it were. And I want to emphasize here, I tested just the sample points, but I'm extrapolating the conclusion to the whole infinite cells. And then in this case, the question was, does there exist an x for this to be possible? So the x's where there does, the values of b where there exists an x are exactly the blue lines here, b less than -2 and b greater than +2, including the points -2 and +2 themselves. So here I have eliminated that existential quantifier. I've got the equivalent mathematical statement, which is not quantified, but I haven't done it using floating point. I haven't done it using numerical computation. Everything about this is done using algebra. So that shows you how to eliminate existential quantifiers. What about eliminating universal quantifiers? Well, we simply take this fundamental logic relation, which says that if you have a universal quantifier, it's the same as negating the existential quantifier applied to the negation of the statement. So we can essentially boil down universal quantification into existential quantification. And indeed, if we have our original example from the first slides, that was the example with universal quantification and greater than 0. So this fact says that we can just study existential quantification and less than or equal to 0. And so we simply have to, if we solve that, that's the example from the previous slide. And so if we want to get the solution to the original problem, we just have to negate the answer from the original slide, which says that we have the answer we found originally. And this is hopefully why you can see now cylindricity is useful, because it makes this projection of cells easy, and it makes the negation of cells easy. So it gives us a structure that makes these tasks easy to do. Now, I'm not going to go into how to build a CAD. We don't have time for that today. I would just say it uses a lot of computer science, a lot of programming, and a lot of mathematics. And mathematics is kind of proving that the conclusions that we draw at sample point are valid across the cell. But I haven't got time to go into the full details of that today, which are a bit complicated. If you're interested to try this out yourself, just as do some examples, well, if you happen to have the two main computer algebra systems, Mathematica or Maple, in your school or university, they all have packages built in to do this. If you don't, there's free tools available online. QuetCAD-B is probably the best, and it can be used as a sub-package of the Python package Sage, or it can even be used in your browser as part of the GeoGebra Discovery package, so you don't even have to install anything to use it there. And I'll share these slides with Amir. I'm sure he can share them with you if you're interested to play around with this stuff. So it all sounds good, but it's not all good. I haven't told you the bad stuff yet. So the problem is that although in theory this is fine, it's really, really, really expensive to build a CAD. So building a CAD is something that grows doubly exponentially. Now, I'm not going to go into full detail about that if you've not heard of it, but maybe you've heard that word exponential. It was applied, for example, with the COVID-19 pandemic. COVID-19 was a disease that was exhibiting exponential growth in our populations, and that was really, really bad for our health systems. Well, doubly exponentially is even worse than COVID-19 in terms of growth. And these pictures produced by my PhD student, Terizo, show in piles of grain exponential growth on the right and doubly exponential growth in the left. And the message is you get to the gigantic pile of grain in just a few steps. And so what does that mean in practice? It means, if I'm doing CAD for 3, 4, maybe 5 variables, it's okay. But suddenly I'll go to 6 and I've got a pile of grain that I just can't compute. So we call that the doubly exponential wall. And I'm going to finish today by talking about some of the ideas we have for pushing back the doubly exponential wall. The picture here, I asked not ChatGPT, the OpenAI image generator. So it's an AI image here of I think I typed AI breaking down a wall. It gave me this picture because one of the ideas we've been looking at is the use of machine learning to help us here. Not the only one, though. Okay, so I'll talk first about that then. So machine learning or AI, you've probably heard this. It's been in the news an awful lot lately. The basic idea is you use statistics and very large quantities of data to learn how a computer should do something that it's not actually been programmed to do explicitly. And this is, when people talk about AI in 2024, they're really talking about machine learning. And it sounds really odd to apply machine learning in mathematics because machine learning is, by its very nature, probabilistic. It only ever gives you at best, 99% accuracy. It's never 100% right, and that's fine if you're making pictures or deciding if making classifications, but not for mathematics. For mathematics, we want exact answers. However, the idea we had was that machine learning techniques could be used to make choices within our mathematical algorithms, choices that are not critical for the mathematical correctness, but can still really affect how quick those algorithms are. So one example of such a choice for CAD is the variable ordering. So I told you that these cells are stacked in cylinders. So if you think of the cylinder as going from top to bottom with this polynomial, then it's a really, really simple CAD. There's one orange cell, a black cell, a cell, and then a green cell on top. But if I thought about the stack going from left to right instead of up or down, I actually end up with a much, much more complicated CAD. Now, both of these CADs are fine for doing quantifier elimination on this polynomial, but it's obviously going to be a lot quicker if I use the one on the left than if I use the one on the right. So, how do we make this decision? Well, the honest answer is most computer algebra systems just use a really crude heuristic to decide, and it's not very good. But actually, maybe machine learning can do something better. in the interest of time, I'm going to skip that slide and just kind of give the high-level idea here, which is that we've experimented with lots of different machine learning models to make this prediction, and they do tend to be able to do better than the simple guesses that we used to make. We've experimented with lots of different ways to represent the polynomials for the machine learning. That's probably the hardest part of the problem. It requires a lot of thought, and I don't think we're perfect on that yet. I think there's a lot more we could do. We've looked at different ways to frame this problem, what type of machine learning to use. There's lots of different types out there. And another really difficult problem is how to best to get training data. So machine learning works by looking at large quantities of data. So how do we get enough data that's able to train machine learning, train AI, while still being somehow representative and meaningful of the type of real-world problems we want to solve? And most recently, Teresa, another one of your hosts, has been looking at the use of explainable AI tools to try and extract algebra code from that's independent of the machine learning, can be used simply as algebra rather than with any dependency on the data. So yeah, with the first group to have looked at pretty much all of this stuff, and then I'll finish with just another couple of slides. No, I can see I've only got 2 minutes left, so I will finish on time. So the other thing we've been looking at recently is the use of SAT solvers. So SAT solvers is a completely different area of computer science. It's nothing to do with algebra. They're to do with solving the Boolean satisfiability problem, which probably haven't heard of, but it's a famous computer science problem. It's meant to be one of the hardest problems in computer science. And then the weird thing is there's tools that solve this really hard problem really quickly. So it's kind of a bit confusing from a mathematical point of view. But it's based on very sophisticated search algorithms that seem to stumble upon solutions quickly when they really have no right to. And what we've done is kind of redesigned CAD in the last few years so that we're taking this approach that is inspired by SAT solvers of searching for our solutions kind of not randomly, but in a sophisticated way, rather than building up entire CADs in one go. And often we can find solutions far quicker this way. Not always, and that's the crucial point, but often. Okay, so I won't go into full detail there, although I'm happy to ask questions if people have it. But if I'm going to summarize now in my final slide, one of my main points: computer algebra is an interesting, active field of research using both algorithms and algebra. So I'm pretty sure that Al Khwarizmi would have been interested in it. Quantified elimination is a really powerful tool in mathematics that can be really useful if you're doing science and engineering problems. And although the mathematics here was established half a century ago, there's been lots of progress recently, not just by my group, but by others too, by mixing it up with other areas of algorithms, SAT solvers, and machine learning. So I guess my message to the young researchers out there is to look, when working on your problem, look for inspiration from the other areas and see if you can transfer that to what you're working on. And with that, I will finish. Only 1 minute left.
Thank you, Dr. England, for the nice presentation. I personally enjoyed, and I'm sure that other people also enjoyed. If anyone has any question, they can unmute themselves, ask, or write in the chat. Does anyone has a question, or should I go ahead myself?
Hi, maybe I can ask.
Okay, sure. Alexander, please go ahead.
Question. Thank you for your talk. It was a very nice talk. I was just wondering, as you mentioned at the beginning, numerics, yes, and then you said, okay, we use algebra. Maybe is it possible to combine numerics and algebra so that you make the right error, yes, the correct error, so that you don't do too much error, so that the final answer is correct? Maybe.
Yeah, there's I spoke as if there were two opposing armies: numerical computation and symbolic computation. But actually, there's symbolic numeric computation where we apply both of the paradigms together. So that's a wide field of interest, and There are one of the most efficient implementations of CAD, the one in Mathematica. The reason it's so efficient is because it uses floating point computations when it can guarantee that it's safe to do so, and this allows it to be a lot quicker than some other implementations that are always working algebraically, while still guaranteeing correctness and using algebraics when it needs to. So that's one thing. And then another thing that Amir's used to is sometimes he's trying to do stuff with algebra, and it reaches a point where the algebra is just too slow. But then maybe you can leverage it by doing some numerical computation on top. So you get some certainty, but not full certainty. So yeah, absolutely, the two can work hand in hand to go further than they can on their own.
Okay, thank you very much.
Said, do you have a question?
Yes. Hi, Dr. Matthew.
Hi.
I really enjoyed your talk. If you saw my poster, I was looking at computer algebra algorithms. I heard name of several of them, such as Grobner basis, resultant, triangular sets, and CAD. And I heard that quantifier elimination can be done using these 4 tools I named. But are there any more algorithms to use for quantifier eliminations?
So yeah, right. So quantifier elimination. I talked about it today using CAD as the mathematical tool. There is a variant of CAD which uses triangular decomposition, so that can be used. It has some advantages and some disadvantages. Sometimes it can work very nice. The Grobner bases, as a vanilla Grobner bases, they're not really designed for quantifier elimination, because Grobner bases is designed for studying ideals, so kind of sets of equations rather than inequalities. However, there are extensions of Grobner bases into things called comprehensive Grobner bases that can be utilized to do quantifier elimination. So there are tools out there that work based on this, and yes, indeed, there are other approaches as well. So that you haven't mentioned that are out there. The CAD is nice for 2 reasons. So first of all, it's somehow the easiest to explain in a short talk. It has some nice visual properties that perhaps the others don't have. Also, though, it's somehow the easiest to implement. That doesn't mean it's the most efficient, but it can be implemented in generality relatively easily compared to the others, and so it does tend to be the one that perhaps you see in the most systems. But yeah, it's not the only one. That's right.
Thank you so much.
Any other question? No? So maybe I ask one question on behalf of the students who may also watch later when the summer vacations finish. The only speaker who talk about ML is you, so I think it's the best. You are the best person to answer this. For those students who are early in their path, just started their bachelor, and they hear about machine learning a lot of places, and they get interested to start. Do you have any advice how to start, what to do, where to look?
Oh well, wow. Okay. I'm a latecomer to machine learning, so I didn't study machine learning at university or anything. I just kind of experimented with it as an adult, as a staff member. The thing is, machine learning is very, very popular. So there are many resources out there where you can learn it. But as with learning anything, I encourage you to start by learning the basics. Don't try and jump in trying to understand ChatGPT and transformers, because this is very complicated type of machine learning. You want to start by trying to understand the very basic cases of machine learning, basic classification and regression, and build up your knowledge to that. And I think that's probably good advice for learning anything, is to try start by understanding easy cases. And for anything algorithmic, such as computer algebra, but also machine learning, doing is learning. So you're not really learning it until you're writing some code to do it. So if you're trying to learn cylindrical algebraic decomposition, I'd be encouraging you to do examples on one of these systems. If you're trying to learn machine learning, download Python, download sklearn, and start playing around with the different tools there. So doing is learning. Yeah, reading is great, but you also want to do some programming.
Thank you. Any other questions from the audience? Okay, if not, we thank Dr. Matthew again for the presentation.